Okay, let's dive into this. Welcome to today's Explainer, where we're going to unravel a massive medical mystery unfolding literally right beneath the ocean's surface. We're looking at the severe crises threatening our global coral reefs. But listen, we aren't just doing a broad environmental overview today. No, we are stepping right into the shoes of underwater medical detectives. We're going to figure out exactly what is attacking these vital ecosystems and, more importantly, how we can properly diagnose and treat them.
So, when coral turns white, is it dead? Now, you might think that has a simple yes answer, right? Especially given those really dramatic, heartbreaking photos we always see in the news. But the reality is actually far more complex. A white reef is essentially a patient presenting a critical symptom. But the underlying disease, well, it could be one of several very different threats. Diagnosing it correctly is absolutely crucial. It's the key to saving the reef.
To solve this, here is our dossier. We'll start with Section 1, a coral reef crisis. Section 2, rapid versus slow necrosis. Section 3, the bleaching distinction. Section 4, diagnosing in the field. And finally, Section 5, response and recovery strategies. Let's get right to it.
Section 1, a coral reef crisis, the patient in peril. Let's establish the baseline state for our patient. Our coral reefs are currently facing multiple and often overlapping threats. When a diver or marine biologist swims over a reef and sees that it's just turned completely white, or maybe they just see bare, exposed substrate, they have to ask, what is actually attacking this colony? You see, it's not always just a warming ocean. Sometimes reefs experience highly infectious coral diseases that spread like wildfire across colonies. And the real challenge here, these different threats visually mimic each other. Without extremely careful field observation, it is incredibly difficult to distinguish between an infectious disease and a non-disease stressor.
Section 2, rapid versus slow necrosis, the tissue necrosis twins. Time to meet the first two infectious suspects in our mystery.
Now, what's really fascinating and terrifying about our first suspect, rapid tissue necrosis or RTN, is the sheer speed of it. RTN is characterized by a swift loss of living coral tissue. We are talking about a sudden, super aggressive shift from healthy, vibrant tissue straight to bare skeleton. Observers can literally watch a fast advancing boundary moving between the healthy and affected areas. The tissue might look like a darkened or pale strip that just peels away or entirely disappears, leaving nothing but exposed substrate. And the scariest part? This entire deterioration happens over hours to days. It's a completely ruthless wipeout that puts all the adjacent healthy colonies at extreme risk.
Okay, now let's contrast that with our second suspect. On the one hand, we have RTN, that abrupt wipeout over hours or days we just talked about. But on the other hand, we have slow tissue necrosis, or STN. STN is a completely different beast when it comes to pacing. It involves tissue loss that develops much more gradually. It's a less dramatic pace, expanding over longer intervals. But make no mistake here, it still results in exposed skeleton and the tragic loss of living tissue.
This thought right here gets to the absolute heart of the diagnostic challenge. Because both RTN and STN produce the exact same end state, a dead skeleton where living tissue used to be, the practical distinction for responders is usually the rate of change. Responders really have to be meticulous detectives out there. They rely heavily on detailed field logs, they need precise timestamps, estimates of the affected surface area, and continuous photo series just to evaluate if the pattern they're seeing matches the terrifying speed of RTN or that slower creep of STN.
Section 3, the bleaching distinction, the third suspect. Now we pivot to the third, and honestly, the most widely misunderstood suspect attacking our patient. You have likely heard of coral bleaching, right? But let's define the precise biological mechanism here. Bleaching occurs when corals actually expel their symbiotic algae, known as zooxanthellae, due to major stressors. Usually this is thermal stress from warming waters, but it can also be triggered by prolonged high light or poor water quality. When those algae are expelled, the corals look white, pale, or totally washed out. But here is the absolutely critical distinction. Unlike RTN or STN, which are progressive infectious diseases that destroy tissue, bleaching is just a stress physiology. The tissue is not necessarily dead at the time of observation.
Which leads us to a massive plot twist. Bleached corals are pale, yes, but they are still alive. In fact, if environmental conditions improve quickly enough, bleaching can actually be reversed. However, and this is a big however, because they are in a heavily stressed state, they become highly vulnerable to opportunistic pathogens. So, a bleaching event isn't necessarily a death sentence right off the bat, but it severely weakens the coral's immune system, which vastly increases its vulnerability to the fatal diseases we just discussed.
Section 4. Diagnosing in the field, running the diagnostics. Let's look at how responders actually figure out what's happening. And this brilliantly illustrates the strict observational checklist that dive teams and scientists rely on to avoid dangerous misclassifications. Let's walk through it. First up, timeline. They have to check if the lesion boundary moves over hours or days. Second, lesion appearance. Are there sharp necrosis margins indicating disease, or more of a generalized paling indicating stress? Third, color and tissue status. Is the skeleton visible because tissue was physically lost, or is the tissue bleached but still physically intact? Fourth, local context. They evaluate recent heat stress, wave impacts, sediment, or nutrient changes that might be weakening the corals. And finally, spatial pattern. Is the effect clustered, which strongly suggests an infectious spread? Or is it widespread, indicating a broader environmental stressor? This kind of standardized monitoring is absolutely vital.
Section 5. Response and recovery strategies, triage and treatment. Once the field diagnosis is made, it is time for action.
So the crucial point is that the response entirely depends on the diagnosis. The protocol generally follows 3 steps. Step 1 is rapid assessment, getting out there, mapping out the affected colonies, and estimating the area. Step 2 diverges based on the actual threat. If it's an infectious disease like RTN or STN, the goal is containment to protect the healthy colonies. But if it's bleaching, the focus completely shifts to stress mitigation and basically hoping conditions normalize. Step 3 is the long-term game, continuous monitoring, updating those maps, and actively planning for restoration once the immediate crisis has passed.
Let's look at a few of the specific treatments managers can deploy. To help the coral fight off these threats, responders work hard to reduce local stressors, things like sedimentation and pollution inputs. They might even limit physical disturbance by coordinating strict dive or boat access rules so the fragile reefs aren't touched at all. For bleaching, they align with broader thermal monitoring, since recovery windows tied directly to heat exposure. And after the crisis, regions might implement coral gardening or propagation to literally replant the reef. But remember this, if you misidentify the problem in the field, you risk deploying completely mismatched interventions that won't help our patient at all.
Which brings us to our core takeaway today. Coral decline is rarely caused by just one isolated factor. Temperature, water quality, and disease outbreaks, they overlap constantly. Systematic data, things like consistent transects, standardized lesion scoring, and those incredibly crucial time-stamped photographs, they are our best tools. They support better decision-making. They help managers detect changes early, communicate the risk clearly, and focus resources exactly where they will most improve the reef ecosystem's chances of survival against these recurring shocks.
As extreme heat events become more and more frequent, integrating disease surveillance and stress reduction is quite literally our only clear pathway for recovery. Which leaves us with a really critical question to ponder. As these threats accelerate, will we learn to diagnose our reefs fast enough to save them? The tools and the science are definitely there, but, the clock is ticking. Thank you so much for joining me on this deep dive into the medical mystery of our coral reefs. Keep observing, keep learning, and I'll catch you on the next explainer.